Welcome, everyone. Welcome to our webinar about engineering one Bloor West, which is Canada's first supertall structure. I'm Marion. I'm Central Engineering Lead at ArcelorMittal Steligence, and I'm delighted to welcome you to our webinar and to also welcome my fellow speakers for today's presentation. We have the chance to be with Daniel Snodgrass, who's associate at RJC Engineers, Tim Verhey, Executive Vice President at Walters Group, and Joe Dardis, Head of Pre-Sales Construction Projects, ArcelorMittal North America. So without further ado, we will start the presentation and we will start to dive directly into the projects with a presentation from Daniel. So like I said, Daniel is Associate at RJC Engineers out of Toronto. He specializes in high-rise towers, as well as leading a team focused on large and complex projects. His work creates effective and constructible solutions to challenging problems in dense cities, winning several international awards. Daniel has also presented broadly on RJC's work to reduce embodied carbon and structural quantities. Beyond the office, he is a voting member on CSA groups where he shares and reviews ideas that will shape future standards for Canadian engineering projects. Daniel, thanks a lot, and the floor is yours.
Thank you very much. I'll get started by describing what the project is and how we arrived at the solution. Here you can see a quick rendering from the onset of the project of the tower inside the Toronto context. Since they let me go first, I'll give you a quick context on RJC as well. We have a 75-year history and are the largest structural engineering firm in Canada, with offices also in the US, now in New York and Nevada as well. Overall, the project team consisted of Fosters and Partners as the design architect, core architects as the architect of record, RJC on for structural engineers, and then we were also on for cladding as well, with RWI completing the wind engineering on the project. Tridel has now taken over as development manager of the project. I think it's important to understand the context of the project for why it is and how it became what it is. So here's a quick snip of the project and where it is in Toronto. It's just north of the downtown core and on the edge of what we locally call the Mink Mile, which is a very, very, very fancy shopping district with, I think when the project first started, rents around $1,200 per square foot for residential costs, and $300 per square foot rental costs. And tons of people pass through this corner every single day. It's at the major intersection between the two main subway lines inside the city of Toronto. So there's a lot of foot traffic and then in this high-end shopping district. But the site itself is incredibly tiny, very, 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 very small. And so what did we actually have to do to achieve this project, what were we asked for? Ultimately, how we describe the project internally is this really Swiss watch, this really tiny site with complicated asks and a lot of competing interests. But what we really arrived at was a very simplified structural system to actually kind of achieve this. And so the original ask that when the client first came to us was to have as tall of a building as possible with completely uninterrupted retail space at grade. So because of the premium nature of the corner and the retail focus, they really wanted this completely open retail portion at grade. But to make the project work, you then had to have Canada's tallest residential tower on top of that. And so the original ask was around 300 meters tall and only 21 meters wide. You can see one of the original models that was made to actually show this structure. And so it would have been an 18:1 aspect ratio, and it would have had an exoskeleton structure. As a signature architect, so Fosters and Partners were really involved in design early and what they had a vision for the project, and no corner columns. This is an absolutely astronomical ask for structural engineers. We love cores. We love everything to go straight down. We especially love corner columns. But in the end, we found that the solution that we came up with actually worked to solve all these challenges and work together in a really cohesive manner. So some of the challenges that we had here were the slenderness, is a very tight access to garage. The ramp itself to even get into the garage took up about a third of the site. There's 4 levels of parking. We selected to use car stackers to actually even make as much of the parking feasible as possible, plus a retail concourse, and then all these different uses, right? So we had this lower grade parking usage, this flagship retail usage, restaurant, hotel lobbies, residential lobbies, and then everything up above that. And so we went through tons and tons of different studies. It was under continuous development all the way from 2015 to 2019. Lots of different heights were reviewed, 5 different sets of wind tunnel tests with 25 different runs, just even at this concept stage before we actually got into the full design of the building. And you can see a bunch of the models that were displayed in the city of Toronto at Metro Hall here, just showing all the different forms and shapes that were studied. And so again, you can see this here, some of the wind tunnel tests that are completed on the project, all these different optimization shapes. Again, it makes a huge difference, as we'll show. Just some of the diagrid options that were studied when it was definitely more of a rectangular building and before we stretched it out. And ultimately, we struggled. We really struggled with the diagrid concepts. Tonnages are incredibly high. Toronto, as it still is very much a concrete town. But ultimately, we weren't going to make any of these solutions work without steel as well. And so what we're going to do, here's the Bloor Young station. Hopefully it's renovated soon. So quite busy at rush hour. And how do we simplify this? How do we turn this into a system that we can actually make that's, going to actually make this project happen? And so this is what we arrived at. It's definitely not a diagrid structure anymore. I still see that called that sometimes. But what we really have is a building that is a traditional concrete core building up above. And then really at the base here is where a lot of the meat and potatoes happen in the system. So we have this composite structure that lands on these inclined struts and goes back to this composite structure. And I think that's what we really want to talk to you about today. And the focus of today's talk is on these mega columns and this composite structure at grade. It came down in height a little bit, so 308 meters tall, 30 meters wide. So still fairly slender. It was designed for 330 meters tall. And again, we still have no core going to grade, no interior columns, and high performance concrete. Here's a quick image of the building. So here you can see the composite structure at grade. We've deleted floors, obviously, since we want to be able to see what the vertical structure is. And we can convert into that kind of traditional concrete core structure up above. Those eventually drop away, and we go to a traditional center core system with outriggers. And then we repeat those a couple times before we get to the top of the building where the TMD is at. Again, with this focus on the bottom again, so you can see where all of this composite structure lands on these big inclined steel struts that transfer out to these composite mega columns that are around the perimeters. The system itself just has these 8 core mega columns, as we call them. You can see an image there of the completed space and just how voluminous that space is. The mega columns were originally designed in 2017, so it was prior to broader code adaptation. So we used a mix of standards. We used the Canadian standard, the AIC standard, Eurocode 4, as well as what we call the CTBH guidelines. And we got, you can see there, a range of answers out of those interaction diagrams. A lot of it depended on limitations each different code had to steel strengths. But a lot of developments happened since then, which we'll be talking about at the end of this presentation. But the loads are large. We're up around 300 meganewtons in terms of what the loads that each of these columns was designed to take. This transfer structure is complicated too. So we have this composite core wall system up at the top, and that's transferring down into these inclined steel struts with these really large diaphragm forces that are happening in the plane of the slabs. And so you can see a sample of the ground floor with these really big diaphragms to actually take the tension across the site, as well as working out those shears into the rest of the system. And so one of the first challenges we had to contend with was how to actually connect this all together. And frankly, early on, we're like, you know what? We were talking to some of our partners at Walters, and with Cast Connects, we said, is there just a really dumb solution? Like, I'm a dumb concrete guy originally. Is there just a big hunk block of steel that we could use to actually make this happen? And it turns out there is. Now, of course, we did a lot of VE on those items. So where we originally were assuming about 50 megatons per casting, it came down in weight substantially, and that's work that we did with our partners at Walters. But we had to do a lot of work to really figure this out. So we did a lot of time-dependent work that's really addressed the differential shortening between these steel struts and the composite mega columns, especially the interaction above with all of the concrete work. And we wanted to generally keep everything in compression. So it actually happens that the mega columns generally stay in compression on this building. And it's really the ties that we're trying to limit stresses and strains with to keep cracking down. And again, at this signature retail level, we have some incredibly expensive and fancy pure glass. It spans about 13 meters. And so really to be careful about the shortening of the tower itself to see how all of that pans out to make sure that we don't impact the glass. You can see some quick examples of how those nodes actually turn into a reality, which Tim will talk about a bit more in a second. I won't get too much into the above the podium section, but you can see just some examples from the construction here where we really had to work closely with our partners in rebar forming and steel to really make sure that we could actually fit all of this together in terms of heavy rebar congestion, all of the steel struts, and then just actually converting that load back into the concrete itself. Here's some construction photos of where we started. So we have some very large 3-meter diameter caissons at the bottom, getting up into the podium with the composite steel, and then starting to follow it up with the concrete, and then into the typical tower sections above. Then we come back to steel at the top with a steel crown and a TMD. And at the end of the day, it was Canada's first super tall structure. So we got to the top. Finishing touches are going on the tower now. And I'll turn it over to Tim to talk a little bit more about the fabrication and what went into the process.
Thanks a lot, Daniel. I'm glad to now introduce Tim, who is co-owner and executive vice president at Walters Group, a leading structural steel fabricator and erector headquartered in Hamilton, Ontario, with operations across southern Ontario and in North and South Carolina. He's a structural engineer with more than 35 years of experience in the design, fabrication, and erection of complex steel structures throughout North America. Tim's work spans major commercial, institutional, industrial, and infrastructure projects, with a particular expertise in the fabrication and erection of steel frame high-rise buildings. Tim, the floor is yours.
Thank you very much, Marion. It's my pleasure to talk about the fabrication and construction of this fascinating tower. We'll focus on the below-grade structural steel. We'll then focus on the modular columns, and then very briefly touch on the above-ground steel and the top of house.
I gave you laser pointers. There you go.
So starting with the below-grade structural steel, what we see is at the bottom of these images here where my pointer is, that's the level P2 parking level, and then we have P1, and then we have the ground floor. We'll focus on all of the structural steel, their hybrid columns, hybrid composite. We'll show you what's involved in their construction and their fabrication. Here's a worm's eye view. We're down deep into level P2. There's a fully reinforced concrete column coming up to that green band. That's a transfer plate. And above that, we have these modular columns. The modular columns themselves have 4 heavy A913 jumbo sections inside. They're welded together with link plates. They're all milled on the ends to give us the full bearing, as they are key compression elements, and they're riddled with shear studs to engage with the reinforced concrete. Here we have one in fabrication in our shop. The base plate and the cap plate are fully milled, again, to give us that full bearing. And you'll see that all of the rebar on these columns has been pre-installed in the shop. This was an innovation that was developed collaboratively with our partners, RJC, the construction managers at the time. And it was a huge game changer for this project in terms of saving cost and achieving a very tight schedule. Here we have these very large columns being placed. The left gives a sense of scale. The center, we're dropping it in place with the overhead, with the large luffing crane. And then on the right, you just see, again, sense of scale. These columns are absolutely massive. And had they been fully reinforced concrete, they would have been even larger. Now let's focus on the ground floor. This is the tie system that Daniel referred to earlier. All of the horizontal members in this image are steel plate. They started out as jumbo sections, but for simplicity of connections, we moved to a plate detail. And then they connect to each of the nodes that you see in blue around the 4 sides of the tower, which form part of the mega columns. Here we have all of the lowered steel at the ground level being trial fit. It was critical for us on this project to make sure there was no fabrication misfits or any other quality challenges. So all of this was pre-assembled. And here we see it being placed in the field. We're a steel constructor, so we're responsible not only for the connection design and detailing, but we also do fabrication with our partners, and we do all of our own installation work as well. So here you see an image of the tie steel as it's heading into place. This is another image. This project was built right during COVID, so there was a brief period of time where the project hit pause, but we were able to very quickly, with the motivation of our partners, to get back on track. Now let's look at the main tower. This is ground floor at the base of the image, and then we can see level 3, 4, 5, 6. You can see the large mega columns. If we peel away some of the concrete, here we can see these mega columns. The green image, the green contents of these are the jumbo sections, and then we have all of the rebar. An incredible coordination effort to pull all of that together. Some of the elements, just touching a couple of them. One is the ties we talked about. 2 is a ground floor node. 3 is a mega column. 4 is a node further up at level 3, and then the very heavy diagonals, number 5, and then some of the nodes at level 3, which are noted as number 6. Just focusing a little more, you can see all the interface of the different elements. Here's a ground floor node that Daniel showed earlier in the fabrication shop. All of the rebar is pre-installed. It's all pre-coordinated. All of the couplers that are used to tie the rebar to the fabrications were pre-coordinated. That was all shop fabricated, which saved a significant amount of time and effort in the field. Here we have the node in all its glory. One of the key features of this node is the center plate. It's called an HIB, and that's produced by our friends in Toronto, Cast Connects. This one is 18 inches or 450 millimeters thick. They're manufactured through a casting/forging process. Here you see it coming through the factory, and on the right you'll see one of Daniel's colleagues, Kevin, just marveling at the size of that HIB. Solid block of steel, and its claim to fame is it has completely isotropic properties, so all of its through thickness tension characteristics are identical in all 3 primary axes of the element. So it's perfect for this application. Here's another photo of all the rebar installed in the shop. And now let's go back to site. Here we see the level 3 tie level. We see the mega nodes being installed. We see the huge luffing tower crane that we put on the site. And again, moving along, here's some of the nodes at level 3. Bird's eye view as the tower keeps moving forward. I must reiterate the fact that we used the modular column with the rebar pre-installed was a significant time saver. They went with high strength rebar. I believe it's, and Daniel will correct me, I think it's 55 KSI bar, up to 55 millimeters in diameter. That's huge bar. And to use a crane to install that would have been a significant amount of time. So by able to do that in the shop, we save significant time in the field. Here's stepping back. You see those large 13-meter tall glass panels at the base of the tower. It's just a stunning wide open space, which we can show you here. Column free. It's really a bizarre feeling when you step in that space and realize there's 85 stories sitting above you with no visible means of support other than those diagonal steel members. Here again, this is basically where the structural steel at the base tops out at the top of level 9. And from there, we zip all the way up to the top of house framing. Just a couple of images before I pass it over to Joe. This is all structural steel at this point. The heavy steel truss work is there to support the TMD. And the TMD, you can see in this aerial image taken by drone, it's the steel elements sitting right in the middle of the tower there. And to top it off, here we have again, a 3D image of the TMD that was produced designed by RWDI and Motioneering in Ontario and fabricated by A&H Fabrication, another local company in Hamilton, Ontario. We've collaborated often with them on these types of installations, and there we are. So with that, I'd like to pass it over to Joe.
Thanks a lot, Tim. That was really an impressive work, and impressive to see all of those pictures from the job site and from the workshop. So now moving on with Joe, who is a professional engineer and career advocate for structural steel. He holds an MBA, an MS in civil engineering, and a BS in civil engineering. Currently, Joe serves as the head of pre-sales for construction projects at ArcelorMittal in Chicago. In this role, he is responsible for technical oversight of ArcelorMittal products in North America, spearheads marketing initiatives, champions sustainability efforts, and manages the pre-sales team. Previously, Joe held various roles at the AISC, including Senior Structural Steel Specialist and Steel Solutions Center Advisor. He actively participates in industry organizations such as AISC, SEAOI, and serves as the Materials Assembly Chair for the CTBOH, now CVU. Now the floor is yours, Joe. Thanks a lot for your presentation.
Yeah, thank you, Marion, and thanks, Dan and Tim. And aside from the excellent structural engineering and fabrication on the project, the other thing that made this design possible was the high-strength steel, or A913 high-strength steel used. This is a steel with yield strengths up to 80 KSI or 550 MPa. It's got very good weldability characteristics, and all of these things provide significant benefits throughout a project. Tim, I think you need to give me control here. There we go. So what makes A913 different than your conventional steels is quenching and self-tempering. And this is where the additional strength comes from. And this picture on the left kind of tells the whole story. If you look towards the left-hand side of the left picture, you'll see steel coming directly off the rolling line, and it's glowing orangish yellowish. It's 1600 degrees Fahrenheit. So it's just been rolled to its final shape size. Then you'll see it enter a QST, or quenching and self-tempering bank, where it's rapidly quenched along all of its perimeter. You can see on the right, there's a cross section where that's happening. So what's happening there is, as you're quenching it, you're rapidly cooling that section, and that's refining the grain of that piece of steel. And that refined grain increases your yield strength significantly. But you don't quench it all the way through the cross section. You still leave that core, kind of in the inner portion of that steel hot. So you can see it leaving the QST bank in that picture on the left, and it's dark all around that piece of steel. A few seconds later, it starts to glow orangish again. So what's happening is the heat retained within that core of that piece of steel then migrates back out to the surface. That's the self-tempering process, which brings a lot of ductility back into that shape. So you quench it, you get your increased yield, and then it self-tempers and removes a lot of that brittleness to give you a very high-strength material that still performs similar to our conventional steels as it relates to ductility. We'll have to go to the next slide. Now, the other thing that's different is, because QST gives us all that additional strength, we actually don't need nearly as much carbon in A913 relative to A992 or our conventional A572 grades. So you'll see there down at the bottom, our max carbon percentage is significantly lower for all A913 grades. It's about half for grades 50 to 70, and then about 2/3 for grade 80. And ultimately, what that means is you're putting less carbon in the steel. It's not as hard. And there's less precautions that need to be taken when you're going to go weld that piece of steel, which ultimately results in less preheating of that steel while you're welding it. And if we go to the next slide, I'll show you exactly what we're talking about. So if you look at this chart, the preheats for A913 are generally a lot lighter than your conventional A992 or A572 grades. For grades 50, 65, and 70, you often don't need to preheat at all, And for grade 80, the preheats actually match A992 and A572 grade 50. So you're getting all that additional strength, but you're improving your weldability and not having to preheat that steel nearly as much, or just the same as A992. So there's a huge weight savings there by using an increased yield strength, but you're also saving on the fabrication end as well in a lot of cases. Next slide, please. The most obvious and common example of when to use A913 is strength-controlled elements. Gravity columns are the most typical example of that. You can just kind of see here from this example what happens as you increase your yield strength and go up to the higher grades of A913. So our initial design in 50 KSI steel, in this example, we have a 14 by 500. And as we go up the line and increase our yield strength, we get down to a 14 by 342. So we can save 32% on the weight of that material just by going all the way up to A913 grade 80. So the cost savings on that is massive. But there's also a lot of hidden benefits that aren't that obvious when it comes to weight savings and using a smaller section size. So for the structural engineers out there, think about what a CJP weld looks like on a 14 by 500 versus a 14 by 342. That's a massive difference in weld size. So you're about half of the weld volume on a 14 by 342 relative to that 14 by 500. That is a lot of labor hours just going into that weld. If you've ever seen a CJP weld, you understand the massive scale of this, particularly if you're welding it in the field. That cost savings can be really, really large and impactful. Also, just using a smaller shape has a lot of other benefits. You're not moving that big. You're moving a smaller shape around the shop. You're erecting a smaller shape. You're transporting a smaller shape. So there's these waterfall benefits that really you don't initially see during design, that you will see throughout the different phases of the project that really emphasize the benefits that A913 brings to the table. Next slide, please. Now, on One Bloor West, all these things were true, but also some of these other hidden benefits pop up that might not be so obvious. Now, Tim showed a bunch of pictures of these columns assembled in the shop, so you have a sense of what these actually looked like. Now, what's really important here is that these things weighed about 46, 47 tons. So these were not light crane picks by any stretch of the imagination. Now, the maximum crane capacity on this job was 50 tons. So this is where A913 was really critical, because if conventional 50 KSI steel was used inside those mega columns, you would have been way north of that 50-ton max crane capacity. So yes, it saved weight and that saved money on the material, but you also saved a lot on not having to splice a column that looks like this, which I can't even fathom what that splice would look like. But it would have been an extremely labor-intensive and an expensive process, or having to bring in a different size crane with a much higher capacity. So these are some of the hidden benefits that aren't necessarily obvious at the onset. Yes, there was a weight reduction, but there's also these constructability advantages that we don't necessarily see right from the jump. And we can look at the next slide too. And Daniel did show this briefly on the size of the mega columns, the initial solution, which was reinforced concrete, versus the mega column solution. And that actually brought a lot of square footage back to the project. So just the difference in size of the footprint of the mega column versus the reinforced concrete column isn't something to ignore. And I think that is often ignored, and we don't take that into consideration. So if we just look at the first few levels, we gained about 519 square feet back just from that column footprint. Now, you might see that number and say, okay, that's maybe the size of a studio apartment. But in terms of rental rates, it doesn't really rent at the same price of a studio apartment. As Dan kind of illustrated, this is a very, very high price district, a super high end retail district. That 519 square feet is going to generate that revenue for the lifetime of this building. And that will be impactful over the holding period of this building for that building owner. So not something to ignore. And I think something that, this project really brings to light that concept and how we should pay a little bit of closer attention to it moving forward. We can go to the next slide. Now, if you are a structural engineer and you are looking at designing with A913 and want to know what things you should consider, I'd say step one is to download this chart from our website. You want to know what sizes are available in A913 and what sizes are available in what grades of A913 as you start your design. This chart's really handy just to pin up in your office. Everything in red is available up to grade 70. And everything in purple is available in up to A913 grade 80. So you always want to reference size and availability based on that A913 grade. Also, keep in mind, once you get below about 100 pounds per foot, A913 is not available. So that because of that QST process, you have to have a thick enough cross section in order for A913 and QST to work, which is why you see availability start with those bigger section sizes. There is no increased lead time by speccing A913 over a common grade. When we roll A913, it's the same exact roll schedule as A992 or your conventional steels. It's just a matter of turning on QST or turning off QST. So there is no separate A913 grade 65 schedule, A913 grade 80 schedule, A992 schedule. It is all the same schedule. You do not increase your lead times by opting for A913. And we get to North American ports about 8 to 12 weeks after rolling. We can go to the next slide. Oh, another great tip for the structural engineers looking to possibly use A913 in the future is a question we get is what grade makes sense for my project? Is it going to be most economical to design with grade 65, grade 70, or grade 80? And that's a hard question for the structural engineer to answer, particularly without a fabricator involved in the project yet, showing them cost differences between your savings with 65, your savings with 70, and your savings with 80. So a strategy we have seen used effectively quite a few times in North America is providing options, providing a double or a triple column schedule and letting the market decide what's most effective. If you show a size in grade 65, show a size in grade 70, and show a size in grade 80, you can send that out to bid and you can let the fabricator community add their value and tell you what the most cost-effective option is. If the lowest bid comes in using grade 80, then the most efficient design is using grade 80. This is a really great way to do it because it essentially guarantees the structural engineer will provide the most economical and most efficient option, but it also eliminates any risk from the structural engineer in possibly making the wrong call or then getting feedback from a fabricator that we don't know how to process this material or weld this material. So it's a win-win for everybody. It allows the engineer to provide a really economical design, and it allows the fabricators to add their value and their expertise from their prior experience. We also encourage the same with our really super heavy jumbo sections, our 14 by 930s and 1000s. If you're unsure, hey, these shapes come from Luxembourg. Does that add any variability to my project? You can show an alternative, okay? You can use a 14 by 1000 or 14 by 808 with a couple cover plates on it. Again, let the fabrication community tell you what's the most cost effective and what's the best way to build it. We can go to the next slide. Now, A913 is not a new material by any means. Grade 65 has been on the market now for about 35 years. There's hundreds of tall buildings and stadiums and not so tall buildings that have used grade 65 successfully. Grade 70 came on board in the early 2000s, and grade 80 was added to ASTM in 2019, and we're up to probably about 10 projects using grade 80. So hundreds of tall buildings around the world have incorporated A913 into their designs. It's been a very effective material in accomplishing really hard engineering tasks like you've seen today. And we're looking forward to a few hundred more here in the next 10 years. So with that, I will pass it back over to Marion, who is the central engineering lead at ArcelorMittal Steligence in Luxembourg. She supervises a team of structural engineers responsible for the pre-design of steel buildings and bridges. She also leads conceptual engineering for projects in the UK and tall building developments worldwide. She holds a PhD in structural fire engineering and a master's degree in civil engineering. She's a member of the CTBUH Europe Scientific and Advisory Group and several Eurocode technical committees. And with that, take it away, Marion.
Thanks a lot, Joe. So now I'm going to give you some details about these composite mega columns that we've mentioned. Daniel, if you can pass on to the next slide, please. Thank you. So starting with the beginning, I'm using here a picture from my former colleague, JC, who took this picture back in 2012 in China when he was watching the construction of the Shanghai Tower. And for this tower, the composite columns were built with steel made of welded plates. And he could see here that the crane was able to lift the elements one floor per floor, actually. So this is a topic that Joe mentioned just before, that because of the heavy weight of the elements, the consequence was the limited constructability due to the crane. If you go to the next slide. And so here we can also see a picture of these elements with the welding on site. So welding these huge elements is actually extremely complex. First of all, you need to apply a preheating for thicknesses above 32 millimeters. Then in windy conditions, it is mandatory to build a tent around the welding zone to protect the welds. So with all of these complexities came the question, okay, do we really need to weld a continuous plate between these sections? Isn't there a simpler way and more efficient way to build these high capacity steel concrete composite columns? Next slide, please. Thanks. So this is how the idea of our composite mega columns came. And we started to work on these large vertical structural elements made of multiple untied hot roll steel sections. So the hot roll steel sections are fully encased in the reinforced concrete, of course, with longitudinal rebars and confinement ties. And they were obviously developed for tall and super tall buildings, so above 300 meters. Designed to carry major gravity loads, but also to resist wind and seismic overturning forces. Thanks to the concrete around, we can just come back, thanks. Thanks to the concrete around the sections, we have additional stiffness, inherent fire resistance, the corrosion protection for the high-strength steel, but it's really thanks to the composite action that we get a higher ductility, better deformation capacity, and a more robust behavior for these critical vertical elements. Next slide, please. But because these mega columns were not explicitly covered in the codes, then we had this idea of launching a research project. You can see here on the slide the research team involved in that research project. And the first step was to conduct a testing campaign with a series of static and pseudodynamic tests. You can see here on the slide the pictures of the scaled specimens with also the formwork on the right side. And the idea was to develop a methodology valid considering Europeans, Americans, and Chinese codes. Next slide, please. Here you can see some pictures from the testing facility. So here is some pictures from the static tests. The actual capacity of that testing facility is 20,000 kilonewtons, so that's pretty huge. And with the picture on the right side, you can also have this feeling, this idea of the magnitude of the testing facility. And the test could demonstrate a good load-bearing capacity, good ductility, stiffness, but something also really important to assess was the good interaction between the steel and concrete. So the fact that we could achieve the composite behavior. After these experimental tests, experimental campaign, some numerical modeling took place with FEM. The idea was to extend the scope of the analysis, so to generate more scenarios, more than what was tested within the testing facility. So both the static and dynamic tests were modeled. And from all of that, a design methodology could be validated, a simplified design methodology based on European, Chinese, and US codes. And this design methodology was also peer-reviewed by the companies that you can see here on the slide. Now, if we move on, we see here the cover page of the CTBUH book that holds all the details of these research programs. So if you're interested to know more about the test, about the numerical work, also the simplified method, everything is described in these reports that you can download online using the QR code or just typing the name of the book. And from this, some things have changed because this took place a couple of years ago, but we are now developing a mega column pre-designed software. It works considering a cross-section discretization in fibers, and using this software, you're able to get the resistance checks, the interaction diagrams in 2D, but also in 3D. The software will generate a report, and it considers that the plane section remains plane, as it was demonstrated through the experimental campaign. Next, please. Now, just a couple of screenshots just to show you a bit what the interface looks like. It's pretty user-friendly. Here you can see how to define the geometry, to select the hot roll steel sections, the steel grade. If you go on the next slide, you can see here that it works with this discretization in fibers. We can evaluate the strains, the stresses, and the forces in the cross-section. Next slide, please. This is to show you the type of NM interaction curves that you can get using the software. Here it's an upgrade by comparison to the simplified method in a sense that you can get the 3D curves as well, not only the 2D curves. And of course, in the end, you get all the design checks. Buckling is checked as per Eurocodes, but for the critical buckling load, the EY, so the flexural rigidity, is reduced as it was a result from the associated research project, and it's a methodology which is also described in this book that I can type in the chat, which is the Design of Hybrid Structures by André Plumier and Hervé Degé. And the software also allows you to compute the minimum required shear connectors to ensure the composite behavior between the steel and the concrete. Now, one last slide to conclude about these mega columns. So as mentioned by Joe previously, one of the challenges in tall buildings is that we try to decrease the size of the column to increase the net floor area. We have some established solutions on the market, but they involve high costs, complex welding requirements, preheating, potentially repair, need of skilled staff. And so the advantages of the composite mega columns with hot roll sections is a smaller footprint of the column, but with lower prices, which are inherent to the simplicity of the system, minimum welding, fire protection thanks to the concrete, construction time decreased, and an overall optimization of the section using the composite action. Next slide, please. And now I am finishing these pack of slides just by reminding, for those of you who do not know, that we have published a technical leaflet that covers all of the details mentioned in this webinar. So about the One Bloor West, about all of the engineering behind these emblematic projects. You can download it from the website mentioned here. You can also reach out to us and we can send it to you by email. We'll do that with pleasure. And now I think we do have a fair amount of time for the Q&A. So I will now start by opening the chat box. Just bear with me a second because I cannot see it anymore. Could see it a minute ago. It disappeared. Maybe Joe, if you can open it.
Yeah, I think if you get rid of your control of the screen, it comes back.
All right.
But I can take the first one here. It's regarding A913 grade 80 steel. What's the cost per ton over conventional steel? Okay, great question. Very common question. So for grade 65 and 70, you'd probably be looking at 2 to 3% in terms of a cost premium. And for grade 80, you'd probably be looking at 4 to 5% on a cost premium. So sub 5%, which is kind of strategic. We really want to make it so it's the cost premium doesn't really factor into the decision. If you're saving 30% on weight and your cost premium is 5%, the economics will always work out where it's kind of a no-brainer if it's a strength controlled element and it's heavy, that it makes sense to go with the higher strength. So good question. There is a cost premium, but your weight savings will always outweigh your cost premium.
Thanks, Joe. I can now see the questions. And the next one is, I think, for Daniel. Someone says, hi, we know Toronto is a low seismic hazard zone, but we are curious about any seismic design consideration.
Yeah. No, that's a great question. Yeah, we are low seismic. Well, it's changed with the most recent code. With the most recent code, we actually, I think, would need to consider some moderate ductility in the tower. But for us, regardless, it's a very wind-controlled tower. And so at the base, it's actually working elastically. Like we're effectively taking the maximum earthquake elastically, but we still did consider the weak story and stiffness checks. The braces are so stiff because of the high strength steel and everything else that there is tremendous capacity even with cutting the core out of the bottom of the building. And so it wasn't something that we were overly concerned about.
Thanks, Daniel. Then another set of questions, actually, there are 4 questions from this attendee. First one is, what is the approximate quantity of welded plates used in the projects and jumbo sections quantity?
That's detailed. I can't remember plate versus jumbo off the top of my head. The total structural steel content, I think, for just the base was around 3,500 metric tons. And so there's a fair bit of steel there. Most of that was in the jumbos. If I had to remember, without Tim opening up his tender spreadsheet, it's probably 50-50 or something high on the jumbo side. One of the things that we did do together was that value engineering proposition to change what we had originally designed to be jumbo sections, even encased in the slab for those big tie forces, and instead change it to those big flat plate sections. Even outside of the space savings from switching and just being able to coordinate and work around the rebar better, the connections to the mega columns and the braces became much more practicable as well. So even if we switched, for example, like Joe was saying, to a completely concrete section, we would have a lot of difficulty and we would still need some pretty fancy nodes to connect ultimately what's going to be a steel tie force together. And so these steel tie forces, the jumbo sections coming down through the composite section, and then the inclined struts together all really kind of pushed into wanting the strategy that we arrived at with the plates and the slab. Really those high integrity block nodes that Tim talked about are working as bearing plates, they're working as tie connection plates, they're working as concrete and the diagonal bearing plates, and then a pass-through plate effectively for the jumbo sections as well. So they're really doing a lot of heavy lifting. And so between the high integrity block nodes, the jumbo sections, and the plates were kind of the main material I think used down at the bottom.
Okay, thanks, Daniel. Another question from that attendee, since it was mentioned that it is not a diagrid system, could you clarify the exact structural system adopted?
Yeah, so it really is that composite hybrid structure system. So at the base, it is like a steel braced frame system effectively, and then it transfers into this composite system, and then above that, it's a center core and outrigger system. So it really is 3 different systems depending on the height of the building that you're looking at and transitioning on your way down. The diagonals that you see on the outside are just concrete hangers for the corner columns. At the same time, as much as they weren't required laterally, they do quite a bit of work for us in terms of the structural system, because all of the corner column loads and also the center column loads transfer every 21 floors, or every 6 floors in terms of the corner columns. All of that load keeps getting dumped back onto those mega columns. So like I said at the beginning, where we actually have mega columns that don't actually see appreciable uplift, that's because we keep putting that load back into those columns and keeping them compression. So it improves the stiffness, and it also improves quite a bit the efficiency of those columns, since we're able to use these big stocky columns to do what they do best. And then the corner columns are quite light. There's these little tiny like foot columns basically. And some of the floors actually don't even have a corner column. So some of the premium suites, mechanical offset levels, don't have a corner column to contend with. But that expression that you still see on the outside of these diagonal hangers, some people still see that as the diagrid system, but it's not, because it's not part of the lateral system strictly, right? Mm-hmm. The other thing that allowed us to do, though, was to have those mechanical inlet floors. So being able to pass the wind better around those mechanical inlets by having that massing change actually made about a 20% difference in terms of the lateral performance of the system, allowing us to really decrease the size of the TMD, as well as the general weight of the structure as well. And so that's where those like RWI and the wind effects can become quite prominent at heights like this. At one point, I think we looked at about 9-10 meters to the tower, which would have been only about a 3% height increase, but it was about a 15% overturning moment increase. So at these heights, you really got to be cognizant of your system and how efficient it is.
Okay, thanks for clarifying. Now a question for Tim. What was one of the challenges fabricating and erecting the heavy structure at the base of the tower?
Yeah, that's a great question. As Daniel pointed out in his segment about the design of the structure, all of the diagonals and the columns at the base of the tower are essentially in compression. And then all of the tie forces at level 3 and at the ground floor are in tension. And that's where we collaborated to come up with the plate nodes. You'll notice that I mentioned all of that was trial assembled, and that was essentially to make sure that everything fit in the field. And similarly for the columns and all the diagonals, those are 100% milled bearing surfaces. So it was critical that we had very, very tight quality control procedures in the fabrication shops to make sure that when all of those tight compression elements came together, all of those joints, and some of them were 3 feet by 3 feet on the diagonals, 8 feet by 8 feet on the columns, that all of those were in tight, full bearing, full contact with no gaps. So quality control was, I would say, the greatest challenge for that lower structure as far as the fabrication.
Okay, thanks, Tim. Moving on with the next question, is there an increased lead time for A913 versus conventional grades or a similar shape size? For you, Joe?
Yeah, simple answer is no, because A913 and conventional grades will roll on the exact same schedule. So when the mill is scheduled to roll a 14 by 500, let's say, that 14 by 500 can be rolled as grade A992. It can be rolled as grade A913-65. It can be rolled as A913 grade 70 or 80. So there is no lead time difference. It's the same schedule. It's the same schedule that we post every Monday on our website, regardless of what that grade is.
Okay, thanks, Joe. Now a question about the software. Is it gonna be released externally? So we are still working on finalizing the software, but it is our intention to distribute it externally, so it's gonna be available for free. And we are actually going to enter soon a testing phase with structural consultants. So in case you would like to test the software, feel free to reach out to us and we can discuss to give you limited access to participate into the testing phase of the software. Another question now, was a time history analysis conducted on the building to evaluate the dynamic performance of the discontinuous system?
Time history analysis is definitely done in terms of all the column shortening and the effects, particularly wind sway effects, but not an earthquake time history. So for this building, we're very, very focused on the column shortening at the base. There's about I think 3 or 4 inch gap off the top of my head for the glazing at the bottom. And so we're very much keen on how does the actual sequencing of the structure. If we did just the steel first and then the concrete, or if we do jump the steel farther ahead, follow up with the concrete, how far ahead we get. We were very cognizant of how that could change our actual shortening and the loads at the bottom of the tower. So in particular, I think there's about a 15-20% delta between the loads and the mega struts, for example, just based on the concrete shortening over time. But in terms of earthquake, there wasn't a nonlinear time history analysis. It's just the static elastic time history that we were looking at.
Mm-hmm. Okay, that's clear. And a couple of questions also about the fire resistance of the columns. How was this aspect tackled?
Yeah, so I think you addressed that pretty well. And plus, Joe, like one of the great things and the use cases for these composite mega columns is being able to do what steel's best at and doing what's best for concrete as well. So concrete's wrapped the steel and it's providing that fire resistance rating. I think in our case, just off the top of my head again, I think we're about 3 inches to steel, 4 inches to steel at least. And so we're achieving much higher than typical fire rating for the bulk steel. And then the diagonals that come out of that concrete section, they're just bare steel. And so that was just traditional fire spray at that point. So they will get clad out. So the diagonals will get clad out. And then again, once the steel's buried inside the concrete slabs for the ties, it's protected by the concrete system.
Yeah.
That was a good question.
Maybe time for 1 or 2 last questions before we close the webinar. What was your experience working with the fabricator and cast connects on the nodes? Was there a lot of back and forth iterations, and how did that relationship work out?
Yeah, it's a good question. Like certainly when we started, as I think many engineers would know, we had a nice happy little node in SAP or ETABS where a whole lot of forces were being done. And we kind of had to quickly come up with a concept for how we think this could actually be achieved. I think we're really lucky in the Toronto and Ontario market to have both Walters and Cast Connects local to us, where we were able to kind of have a phone call even before tender and chat with both of them real quick about what they thought about the system and how they could see it being developed. And so the first node concept we had, we developed with Cast Connects even prior to tender discussions. And then as soon as Walters was officially engaged, we were able to again iterate together on those solutions. I think it worked really well, especially because it pushed everyone to really understand better the loading and the time effects of the loading. So we even looked, for example, at the return periods of winds to see what the different loading is and how many cycles it has for if we had to be worried about fatigue for some of these elements. And being able to actually just get pushed to dig into those loads was I think the most important part from the structural perspective, to really refine what we were looking at. And it was I think the first project that we had really done such a large scale analysis with a fabricator to provide all of our load cases and all of our envelopes for them to really kind of drill down and refine the connection design as much as possible. And so yeah, to me it worked out great. And I think again we're lucky to be able to have some of those decisions and discussions at the time of design.
Mhm.
Tim, I don't know if how you felt about it, but I think I think we arrived at a pretty happy solution for everybody.
Yeah, if I could just add to that, one of the key things that made this project so successful was early engagement of the primary trades. So it's not like we went through a tender process, kept all the cards close to the vest, and then when you land the contract, you introduce new ideas to the design team. There was a forum where we could do that confidentially as a bidder to the construction manager, and that generated a lot of very good conversations and a significant amount of innovation. The hybrid columns with the rebar pre-installed, that's a patented invention on this project that we carry. The ties switching from the jumbles to the plate just made so much sense from the fabrication, construction, QC point of view. So just a lot of really good collaboration with all the stakeholders at the right time.
Great. Thanks, everyone. It is now time to conclude the webinar. So I would like to warmly thank you all for joining, but give a special thank you to my fellow speakers, Tim, Daniel, and Joe. It was really great to prepare this webinar with you. And should you have any questions, don't hesitate to contact us. I see that there are some questions from the chat that we didn't have time to tackle, so feel free to reach out to us, or if you have questions later on, feel free to reach out. We'll do our best to answer them. And then this is it. Thanks a lot to all of you.
Thank you very much. Thank you for setting us up.
Thank you. Have a great day.